Okay, so let's move on to a new section. This is going to be section 1.2. 2 is going to call it irreducible polynomials. The basic idea is, how do we define more exotic types of fields to work with? And the answer is going to be, well, we're going to take a polynomial ring and we're going to quotient out by some irreducible polynomial. And essentially, from one point of view, this is what a number of fields are going to look like. But there's more intuitive ways of seeing them. So let's go through what irreducible polynomials are and like how to tell if you have an irreducible polynomial or not. So as usual, we're going to begin with a definition. 1.2.1. Let R be an integral domain. A non-zero polynomial P of x in R of x of degree at least 1 is said to be irreducible if whenever P of x, if you can write it as f of x times g of x for f and g other polynomials, f of x, g of x in R of x, then one of f of x or g of x is in R, i.e. has degree 0. One thing to note is that this is slightly different from the definition of an irreducible element that we had before. And technically, for what we want an irreducible polynomial to satisfy this condition. Before we said an element was irreducible is whenever it factored, one of the things had to be a unit. But for polynomials, we don't want this because we want to avoid something like if I have like x plus 2x plus 4, if I have some polynomial like this, then I can write this as 2x plus 2, say. And I want to still, for our purposes, we somehow still want to say that these polynomials are irreducible, even though somehow it factors, just because technically this isn't a unit. Technically, this polynomial isn't irreducible in the ring R of x, but it is an irreducible polynomial because it factors and one of the things has degree 0. It's just because for the rings of integers that we're going to define later and all these number fields, these sort of factorizations like this don't matter for us. So we somehow want a slightly different definition of irreducible polynomials. So here's an example of an irreducible polynomial. The polynomial x squared plus 1 is irreducible in z of x. You can think that if this polynomial is to factor, then it would have factor of 2 linear polynomials, and then that would mean that it would factor as x minus I, x plus I, where I is the square root of minus 1. But the square root of minus 1 is not inside the integers. So those two polynomials don't exist in z of x. So this polynomial is irreducible. A non-example is like x squared minus 1, because this is x plus 1 times x minus 1. So this is not irreducible. Okay. I've said all of this about my difference of how it differs between irreducible polynomial and irreducible element in a ring. But for fields, these two things do coincide. So I'll just say it like a remark. If F is a field, then an irreducible element in f of x is the same thing as a irreducible polynomial. So the distinction that I'm trying to make between my two definitions only applies to when f is a ring, not just of it. If it's a field, if it's more than a ring, if it's a field, then they coincide. But for rings, you somehow have to be just a little bit more careful. Okay. So here's a proposition that hopefully you've seen before, but if not, we're going to use this as a black box. We'll use it without proving it, because it's basically a standard thing. You must have seen this. I would have seen this in Galois, if you've done Galois theory, or in some of the algebra courses. So I'm going to let f be a field. What do we have? So f of x, the polynomials in x with coefficients in f. This is this ring. This is a Euclidean domain, and therefore a principal ideal domain. So this is a Euclidean domain because you have you can do polynomial long division, and this gives you a Euclidean algorithm. You can divide polynomials by another, and you can check that the remainders get smaller, that the degrees get smaller as you go along. 2, in a PID, the ideal generated by an irreducible element, or by an irreducible element, is prime. 3, every non-zero prime ideal in a PID is maximal. And 4, every principal ideal domain is a unique factorization domain. Yeah, okay, so I've somehow detoured from my irreducible polynomials to now PIDs in general, but they sort of follow from one another in some specific examples. So I somehow wanted to record it here all together. Mainly because I wanted to remind you that you have Euclidean algorithm for this f of x. And then once you have Euclidean domains, these are nice things. And then PIDs are also nice things. So this is maybe things I should have said earlier, but I somehow left it out to here. So as I said, yeah, we have this Euclidean algorithm. So let me just make this remark. What does it mean? So y is f of x a ED Euclidean domain. Why is it okay? This is because we have polynomial long division. What does this mean? So if I have f of x, g of x elements in here, then we can do polynomial long division to write f of x equals q of x, g of x plus r of x, where the degree, assuming that the degree of g is less than the degree of less than or equal to the degree of f, and the degree of r is strictly less than the degree of g. So that this is important, that it's strict here. But if I have, say, two polynomials of degree 4, I can divide one by the other. This is my quotient, okay, and this is my remainder, this is the r. So we can do this process, and the fact that the degrees are getting smaller is that if you go back and look at what the Euclidean algorithm does, this is the same sort of thing but instead of just using numbers, now we're just using polynomials. But what makes it work is this condition here. So how do we create some fields out of these irreducible polynomials? So here's a proposition. Let f be a field, and p of x an irreducible polynomial in f of x. Then f of x quotiented out by p of x. By this I mean, well, the ideal generated by p of x. This quotient ring is a field. So, let me just remind you, what do these elements in this field look like? So I recall the elements in this field look like. You can write it as, well, you have some polynomial f of x plus you have some like remainder, so you have some a of x, p of x. So this is some element in the ideal p of x, and this is just some other element in my polynomial ring. So I can everything in this field I can represent it as some polynomial up to some element in this ideal generated by p of x. You should compare this to this fact that I said before, that if you took the integers and you quotient out by a prime, you get a field. Here you take a polynomial ring and you quotient out by a principal, a irreducible polynomial, and you end up with a field. Irreducible polynomials somehow correspond to like the prime numbers in this case, and then quotienting out by this thing gives you a field. Okay, so this is how, if I gave you an irreducible polynomial, how you can construct a nice field. You take the polynomial ring and you quotient out by the ideal that it generates. But how do you know that you have an irreducible polynomial? So we have lots of ways of checking. So let's give some lemmas that will help us check when an irreducible polynomial is, or when a polynomial is irreducible. So let's work our way up to them. So you've maybe seen this if you've done Galois theory. This is called Gauss's lemma. A polynomial is irreducible in z of x if and only if it's irreducible in q of x. So I can check if a polynomial is irreducible by either checking it inside the rational numbers or checking it inside the z of x. In practice, this is really useful because I'll give you a polynomial and we'll want to know if it's irreducible in q of x. Well, here it might be a bit complicated to do, but I'm going to give you lots of ways of checking the polynomial is irreducible in z of x. And this is what we're going to use. So somehow we'll transfer from checking a polynomial is irreducible here to just checking a polynomial is irreducible here. I won't prove this because this is proven in the Galois theory course, although you may not be taking that course, but if not, we'll just take this as a black box. Here's a slightly different version of this. 1.2.11. This is something called monic Gauss's lemma. But the monic Gauss lemma. Yeah, that's a better name. Let f of x and z of x be a monic polynomial. Recall that this means that f of x looks like x to the n plus a n minus 1, x to the n minus 1, blah, blah, blah. a 0. So monic just means that the first entry is a 1 in your polynomial. So this is what it looks like. So assume that we have a monic polynomial, the f and assume that f of x can be written as g of x times h of x, then with g of x, h of x in q of x, then g and h are in z of x. So may want to say, although you can always multiply through to fix this, but I want g and h to be in q of x, also monic. Then g and h are actually in z of x. So if I have a polynomial in z of x and it factors over q of x into product of two monic polynomials, then in fact these two polynomials have to have been inside of z of x. So you can't if you find a factorization of f of x and q of x, then you found a factorization in z of x, because these factors have to have actually lived in z of x. Have a think about why these are both called Gauss's lemma. Why am I allowing myself to call these two things the same thing? So have a think of why they're related. But with these two things, we can just reduce from checking polynomials are reducible over q of x to checking polynomials are reducible over z of x, which would be great because the fields that we're going to construct are going to be like how we did in this proposition, but f is going to be q, and p is going to be some irreducible polynomial over q of x. And so, well, we're going to take irreducible polynomials over z of x, which is the same thing, and quotient out by that. Quotient q of x by those polynomials. So here's the first way to check that polynomials are reducible. So proposition 1.2.13. If f in z of x is a polynomial, I don't know why I need to write that. It's in z of x, so that's definitely a polynomial. I'm going to let f bar denote its image in fpx. So what does this mean? I.e. Reduce the coefficients of f modulo p. So take look at the coefficients and then just reduce each coefficient mod p, and then that's the polynomial that I'm denoting f bar. So here's the. I'm not started with my conditions yet, so let's start. Let f be a polynomial, and let a polynomial f in is irreducible if we can find some prime number p such that f and f bar have the same degree, and f of x, f bar in fp bar x is irreducible. Okay, this is the first thing we're actually going to prove. But what am I saying here? So if I give you a polynomial with integer coefficients, if you reduce it mod 3, say, and the polynomial you end up with is irreducible, then the polynomial that you started with had to be irreducible. So, and it doesn't have to be a prime, so you can choose, you're free to go along and check your favorite prime that you want. So let's do the proof. So this is logically equivalent to proving the following. So this is the same as proving that if f of x, I'm swapping between f and f of x. Well, f of x is reducible. I'm just taking the contrapositive. If f of x is reducible in z of x, then it's also reducible. In fp of x. And this is clear. Yeah. Clear because imagine if f of x, I could write f of x as g of x times h of x. Then if I go through and just reduce all of my coefficients mod p, I just get my f bar of x is going to be g bar of x times h bar of x. This is my operation of reducing the coefficients. You can check that this will preserve your factorization. So if your polynomial was reducible, i.e. it factored, then when you reduce mod p, it also factors. And so the converse, the contrapositive of this means that if your polynomial is irreducible inside of here, then it has to be irreducible inside of z of x. Okay, this is maybe a cheat. I've not told, it might be useful in some cases, but it doesn't tell you what prime to check. So there's limited use of this proposition, but it will be quite useful for other things. So here's a more interesting criteria. From it, this will prove what you maybe know as Eisenstein criterion, but this technically came before Eisenstein's criterion, and it's slightly different. So I'm not going to prove Eisenstein's criterion, but it'll follow from this proposition, which is called Schoenemann's irreducibility criterion. So this proposition 1.2.14. Schoenemmann's, I don't know if I'm pronouncing it correctly. Irreducibility criterion. What does it say? So I'm going to let f be in z of x, be monic of degree n greater than 0, and assume that there is a prime p and an integer a such that you can write f of x as x minus a to the n plus p times g of x. P, remember, is a prime number. For some g of x in zx. So if you can write your polynomial in this form, so it's just x minus a to the n, where a is some integer, times p times some other polynomial. So assume that we have this sort of polynomial, then if g of a is not 0 mod p, then f of x is irreducible modulo p squared and in zx. So it's going to be reducible in z mod p squared z. This is what I mean by irreducible mod p squared, but it's also going to be reducible in zx. Great. So this, I think, historically, this came before Eisenstein's criterion, and technically you can use Eisenstein's criterion just to prove Eisenstein's criterion, which we're going to do. But this is slightly different, and it has some fun uses, which you might see. So assume for contradiction that f of x was congruent to r of x times s of x modulo p squared. So assume that we had a factorization mod p squared. where without loss of generality, I can take my R of x and S of x to be monic, because I'm working. Well, have a think of why I'm allowed to do this. It's mainly because my polynomial that I started with was monic. So now consider this equation mod p instead. Then we have it turns into x minus a to the n is congruent to R of x, S of x, mod p. Why is that the case? Well, look at what f of x was. If I reduce f of x mod p, this factor vanishes and I'm just left with x minus a to the n. So this f of x turns into this, and then I just have this left. Because I'm working mod p squared, here I'm working mod p, this is fine, because p squared is greater than p. So now, what do we have? So we have some equality of polynomials in f of, so this is in, let me just, to be precise, this is some equality happening in fpx. We have this. Now, since fp of x is a unique factorization domain, we must have the following. We have x minus a to the I. Well, R of x is going to have to look like something like this, mod p, and S of x is going to have to be congruent to x minus a to the j mod p, with I plus j equal to n, and I and j greater than 0. I'm assuming that my factors, I had some non-trivial factorization. So something like this. If you think of what the factors of x minus a to the n are because I have a unique factorization domain, the factors are just lots of copies of x minus a. So some number of copies have to fall into the R of x, and some other number of copies have to fall into the S of x. So now take this equality and evaluate at a. So now if we now evaluate this equality, this at x equals a. So if we take, if you look at this, when we evaluate at x equals a, we see that R of a is congruent to S of a, is congruent to 0 mod p, as I and j are both greater than 0. But now, okay, let's go back to our original thing. So now if we go back to the original thing that we had, f of x is R of x times S of x mod p squared. Setting x equals to a, we see that we have f of a is congruent to R of a, S of a modulo p squared. If you think of what f of a is, so this implies that I have p times g of a is congruent to R of a, S of a, which is congruent to 0 mod p squared, because I've just checked that each of these is congruent to 0 mod p. So each of them vanishes at p, so together they have, here you have a factor of p, here you have a factor of p, so together you have a factor of p squared. But I have something like this, which contradicts g of a being different from 0 mod p. Because the only way for me to, for p times g of a to vanish mod p squared is if p divides g of a, i.e. g of a has to be 0 mod p. So this contradicts my assumption, because my assumption of my proposition was that I had such a factorization and that g of a was not 0 mod p. Okay, so this is a somehow an irreducibility criterion that you probably haven't seen outside of this course. But let me give you a consequence of this, which you hopefully would have seen somewhere else, or you may have seen like oh, 1 second, I'm still not done. So now, since we are irreducible, I've checked that it's irreducible mod p squared. Now we are also reducible in ZX as the same argument of proposition 1.2.13 applies. Great. So now this completes the proof. So okay, let me give you a corollary of this. This is corollary 1.2.15. This is Eisenstein's criterion. So let f of x, let's take some polynomial, let f of x be in z of x be such that f of x looks like the following. It looks like an x to the n a1x plus a0 be such that with let f be like this. Okay, sorry. Be such that f of x looks like this. Sorry. Let me start again. Let f of x be a polynomial and of this form, and p a prime number. Suppose that an is not divisible by, so this first provision is not divisible by p, and an minus 1, all the other ones are divisible by p, and lastly a0 is not divisible by p squared, then f of x is irreducible. Okay, so I have, if I write my polynomial out and I look through the coefficients, if my first one isn't divisible by p, so p doesn't divide this, p divides all of the other ones, but p squared doesn't divide this, then any polynomial that looks like this has to be irreducible. Proof. Since an is not 0 mod p, it is invertible. So let b be any integer such that b is congruent to an minus 1 mod p. So b is congruent to the inverse of an. Then b times f of x. This will be look like xn plus p g of x. I can write this for some g of x and z of x. Just think of what I've done. Because B is an inverse mod P. So when I multiply B times AN, this is 1 mod P. So when I do B times F of P, this AN, it looks like 1 plus P times something. So I can just regroup it, my P times something over here. And all the other coefficients are divisible by P. All of these are divisible by P. So this is P times G of X. So I can write my polynomial like this. Moreover, G of 0 is not 0 mod P, since A0 is not divisible by P squared. So if when I plug in 0, this thing was 0 mod P, then B times this polynomial would be 0 mod P squared. So this polynomial would be 0 mod P squared, which would mean, so this polynomial would be 0 mod P squared, which would mean this A0 would have to be 0 mod P squared. But that's not true because it's not divisible by P squared. Therefore, we satisfy Schoening's criterion, and therefore B times F of X F of X is irreducible, and therefore so is F of X. So if a constant time your polynomial is irreducible, then your polynomial is irreducible. Okay, so here are some examples. One, let's do that. 3x to the 4 plus 10x plus 5. This is irreducible in Z of x by Eisenstein with P equals 5. So if you look at P equals 5, 5 doesn't divide 3, 5 does divide 10 and 5, but 5 squared doesn't divide 5. So by Eisenstein's criterion, this polynomial has to be irreducible. 2, if I let P be a prime, and we let phi P of x to be the following polynomial, you do x to the P minus 1 over x minus 1, which is, if you expand this out, check that this is just this polynomial, then this is irreducible. You may have seen this proof if you've done some other courses, so you might have noticed, but let's write down the proof. Note that we can't apply, we're going to do this by Eisenstein's criterion, but we can't apply it right away because these coefficients here are all 1s. But the thing is to note the following. So note that phi P of x plus 1, this is x to the P minus 1 plus P x P minus 2 P choose 2 x plus P. This is what happens if you replace x for x plus 1 in this polynomial. You end up with this polynomial, which again is now Eisenstein because of properties of these binomial coefficients. They're all divisible by P. This one, and P, there's no P squared there. So this is now Eisenstein at P. So it's irreducible. And so, here's a little exercise. Prove that f of x and z of x is irreducible if and only if f of x plus a is irreducible for any a and z. So here are some examples of irreducible polynomials. Now, how are we going to, I mentioned before that we're going to use these irreducible polynomials to construct some fields. So here's some examples of fields. examples of fields. So let's do the following. Note, so x squared minus 2 is reducible in set of x. You can use Eisenstein at 2 if you want, but this is pretty obvious to see. So by our results, q of x mod x squared minus 2, or the ideal generated by this, this is a field. And you may have seen this field before. This is a field called, well, say q root 2. Or say this is a field, let's be precise, a field isomorphic to, maybe you've seen this in Galois theory. So this is some field which is isomorphic to the field q root 2, where q root 2, it looks like you have a plus b root 2 such that a and b are rational numbers. This is what, as sets, what this looks like. This is the first example of a number field. This is the sort of fields that we're going to be looking at. And in general, we're going to be thinking of them in this terms, written out like this. But it's good to have the underlying mathematical machinery that we think. Sometimes thinking of it as q of x modulo some polynomial, it will be useful for us. Secondly, okay, so we have like the reals modulo x squared plus 1, which we already checked was irreducible. This is actually irreducible over not just the rationals, but it's also irreducible over R because the square root of minus 1 isn't in there. This is a field as x squared plus 1 is irreducible in R of x. Note that, for this to be a field, I need this polynomial to be irreducible in R of x now. So my previous criterions aren't working because I'm working with R of x now. They were all for q of x. But in this case, this is an easy enough polynomial to check. This field, as you expect, is isomorphic to the complex numbers. I say it's isomorphic. These are fields isomorphic to complex numbers. It's not the complex numbers on the nodes. You have to be a bit more careful with it. It's not equal to the complex numbers. It's just isomorphic to the complex numbers. So there's a small subtlety there. 3, if I let p of x be x squared plus x plus 1 in f2 of x, so this is the field with 2 elements, then you can check that this is irreducible in f2 of x, and therefore f2 of x modulo this ideal is a field. Okay, so I'll leave you as an exercise to check that this thing is a field. But this is actually this is isomorphic to the field with 4 elements. So this is isomorphic to maybe what's called F4, or the field with 4 elements. And here's a proposition that we'll use as a black box now that we're talking about these fields. 1.2.20 for each integer n. So greater than 0, and prime number p, there is a unique field of size p to the n. We denote it by fp to the n, I guess. So maybe I shouldn't have called this f4. I should call it f2 squared. P to the n. Conversely, every finite field has size p to the n for some prime and p and integer n. And n in z greater than 0. Okay, so I'll leave it here for now on this section on irreducible polynomials. Next time we're going to look more into detail at the fields that these generate and the field extensions.